Hello, my name is Anthony Kennedy, and this is my Physics 2212 Lab 4 on circuits. The purpose of this lab was to predict the behavior of circuits containing different forms of resistors, including light bulbs and, the arbitrary resistor thing in FET, using series and parallel components, and to measure these outcomes quantitatively using meters such as ammeters and voltmeters. A few of the fundamental principles that were important for this lab was the loop rule, where the total voltage of the system will equal zero, the potential difference, the node rule, where at any juncture, any current in will equal the currents out, even if it splits into multiple paths, the conservation of charge, the definition of steady state, and finally Ohm's law, where V equals IR, or voltage equals the current times the resistance. The results preview for this experiment was that the measurements taken from the FET experiment fall in line with the mathematical predictions. One thing I want to mention is about the system. The system was just the circuit. The outsides was just everything not circuit. The assumptions that were made for this experiment include the wires have negligible resistance, and so does the actual ammeters and voltmeters. Those also have negligible resistance. For the mathematical prediction section, as you see here, the experimental materials was two 1.5 volt batteries, two ammeters, and two resistors, 47 and 100 ohms. Calculating this, just adding the combinant resistance 147, dividing it by 3, you get about 0.02 amps. When the ammeter is replaced with a voltmeter, as I try to, this kind of weirded me out. I don't know why they want us to do this, but the circuit gets broken, so there's no current at all. So there's just no potential difference, and it's just constant throughout the entire circuit at zero, of course. This is the chart detailing kind of what happens in the series circuit with the two resistors as it goes through each series. Of course, from B to A with the two batteries, the potential difference goes up to 3. And as it goes through the two separate variable strength resistors, there's a smaller potential difference drop from the smaller resistor and the larger one from the larger one. However, in the experiment, it still equaled around 0.02 amps, which falls in line with the experimental answer that you saw in the earlier slide. For the circuit modifications where they wanted us to add an ammeter in parallel with a 100 ohm resistor, because it's in parallel, some of the current is not going through the path with the resistor. So the current actually increased up to 0.6 amps. Yeah, 0.6 amps inside the ammeter reading, as opposed to the 0.02 that was typical when I placed it along the line in series with the 100 ohm resistor, which makes sense. And the sum of the individual potential differences you could see from all the resistors is what equaled the total potential difference, the 3. For the capacitor and bulb experiment, where you modify the circuit to have a capacitor and a light bulb, when you connect the battery, the bulb's immediately at its brightest, and then as the capacitor fills up, the bulb slowly dims. When I disconnect the battery and, of course, reconnect the wire so the circuit's complete, the bulb is bright again and then very quickly dims because the capacitor has a finite, at least in this case, amount of charge, so it gets just depreciated and has no charge. However, for the 10 ohm light bulb, it takes 10 seconds for the capacitor to discharge, and for the 20 ohm, it actually takes a lot longer. It takes 18 seconds. You can see this reflected in this line of best fit graph. I have it plotted over time and the natural log of the potential difference over the potential difference over the initial voltage. And it does create a straight line as the experiment had indicated to us, and it's negative as such. The what if questions: if the ammeter was a real ammeter, of course, as the current flows through it, as all things, they have resistance, so you would have just less current, even though it's the same voltage. In an ideal model, it would charge instantly, that being the capacitor. The capacitor would charge instantly. However, in the real model, even though we usually neglect it, the wires do have their own resistance, and that would have to be taken into account, and it would be slower. Thank you for listening to my presentation. Give me 100.